that. I got thrown off by the missing homework assignment at the beginning. Okay, back to normal. So for those people who missed today and you're only getting half the homework assignment, the other half of the homework assignment, you'll have to see that on the slides. And then, of course, you could ask me questions by email. All right, so because Fg equals 2.5, that means that the spring force has to also equal 2.5. So what we're going to do is we're going to put in 2.5 equals K times D, and D is how much it was stretched because of attaching that mass. So this is 0.05. Solving for K, we divide the 0.05 to the other side. I think I have an answer slide, and it comes out to be 50. Once again, I don't grade units on your test, except for that if you have to do a makeup test, then I'm going to expect that you show me the units in the answer. That will count as a point. So take the test on time and everything's normal, and then you get a little bit easier break because you don't get graded for things like units. Question number 25, 0.01 kilogram mass suspended from a spring. So normally the spring looks like this, but then when you attach a mass to it, it looks like this. And on your test, you're going to draw the FG and the FS to show me that you understand what's going on there. The amount of stretch that occurred here is the unknown. We don't know this answer. We do know that Fg equals a 0.01 kilogram mass would be a 0.1 Newton force, right? Weight, you just multiply it by 9.8 or 10 if you want to make it quicker. Then when we go to use the formula F equals K times D, we're going to put in 0.1 newtons equals the K, which is 10 newtons per meter. I'm leaving the units out so that we don't get confused by them when we go to do our algebra. And then I want to solve for D. So to get D all by itself, I need to divide 10 to the other side, and then it kicks a 0.01 back at us. Now, don't think that because this was 0.01, that this was 0.01. That's just a coincidence because of using a spring that had a constant equal to 10. You have to solve it out. Question number 26. Now I've got to remember which one, Nat, you said earlier. I think you said 27. So hopefully I take care of whatever it is you need to. Just put it back in the chat if by chance I don't answer your question well enough. A spring with a spring constant of 5 newtons per meter has a 50 gram mass attached to it. It's pulled down and released and set into simple harmonic motion. What is its period? Okay, so good physics students, which is all of you, you have your cheat sheet, you have your notes, you see that simple harmonic motion is present. So the first thing that you need to know is what is the formula that deals with the spring and its period. That formula looks a lot like the last one, only it's a T sub S instead, equals 2 pi square root of M over K. All right, so then you look to see if they gave you the values that you need. The biggest mistake made on this problem is forgetting to change the mass from grams to kilograms. You can probably expect that. I told you on one of the earlier assignments that I would for sure give you kilograms so that this mistake couldn't be made. That's because those questions were harder. So I don't want you to mess that up. But on this problem here, this is an easy enough problem. I think it's fair for me to keep something in grams because this is typical of what, in fact, this is a lab assignment right here. 50 gram mass, we have springs that are 5 newtons per meter, spring constants. Attaching that is going to cause it to oscillate at a certain rate. It would be fair for you to change that to 0.050 kilograms divided by the spring constant, 5 newtons per meter. Of course, all of those units you're not worried about. Trust that they will work out. Oh, it's Lori that said, sorry, Lori, I will go over those carefully. So now we take the 0.05, divide that by the 5. My calculator says 0.01. Then I'm going to square root that. Says 0.1. And then now I'm at the point where I can say 2 pi times 0.1. And I mean, I want you to put this in a decimal value. So do the math. Somebody could change that into like a fraction or decimal with pi as part of it. I wouldn't mark that wrong, but most of us don't think that way. So to solve that out comes out to be 0.63. Oops. So 0.63 seconds is how long it takes to oscillate. Remember, because I'm going to probably ask this to you on a test, When we dealt with pendulums, a pendulum's period is to swing all the way out and all the way back. That's 1 period. So I'm going to call that 1T. For a spring's period is based on when it starts at the highest point, that it goes all the way down to its lowest point and then comes all the way back is 1 period. It's probably not good to write IT because then it just looks like I'm talking about it. 1 period looks like this. 1 period out and back. So be prepared that I'll probably try to throw something into your test to make sure that you know what the concept is. And question number 27 must be a hard one. I think it is because it requires 2 steps to it. A spring with a spring constant of 20 has a match attached. It's pulled down and released, set into simple harmonic motion. They gave us the period. They talked about a spring. So what we have then is a period equals 2 pi square root of m over k is the formula for a spring. Okay? Now they told us that the period is 0.63. That's boring. We have the same answer as what we had for our previous problem. Equals 2 pi square root of, we don't know what mass is attached, and we have a spring constant of 20. So we're just working this backward. We have to do algebra to pick this apart, but I just want to remind you, Lori, that if you can do this much for me on the test, you're going to get a 3 out of 5, which with the curve really means a B. And then if you can show me a couple math steps, even if you get it wrong, I'm going to probably move that up to a 4 out of 5, which means an A. So even if you mess this up when it's all said and done, a little bit of work, you're good, okay? First thing we got to do here is divide both sides by 2 pi. And then 0.63 divided by 2 pi equals 0.100 equals square root of m over 20. Now you kind of might be looking at this like, this is a lot like the pendulum problems, isn't it? We're just solving for the m instead of the L, but it kind of works the same way. So now my next step is I've got to get rid of the square root by squaring. And so then when you square that, this is going to come out to be 0.01, and then the square root sign is gone. All right. Now, if you make a mistake somewhere along the way and you keep working this all the way out and you get an answer for m and it's not right, I don't think I'm going to take any points off. If you stop somewhere in here because you're like, I don't know what I'm doing anymore, or if you do some really ugly algebra, you're going to lose a point. Let me give you an example of some ugly algebra. There's a formula that says VF equals VI plus A times T. You guys had this on the lab that was due yesterday. And you were trying to solve for A. So you know that VF is 0, and you solved the first equation, distance equals 1/2 VI plus VF times T, and you got that, let's say that you got that VI came out to be 1.5. That was a pretty common number, something in the ones. Bigger numbers is fine too, but you got that VI equals 1.5. Okay, so, and let's say that your original time was something like 4.5 seconds, right? So just making up some numbers. So then you put in 1.5 here plus A times 4.5. I saw in a couple of people's papers where they just said that A equals 3 or A equals 6. I'm not sure if that was a good choice of numbers for me to pick, because the problem is when you do the division, if you did the division backward, you could get 3, and that's not bad math. So I'm going to change this. Please forgive me. Let's change this to a time of, just make it up, 5.5 seconds. Okay, that wasn't unreasonable. I did see some times like that. So let's change this to a 5.5. These are the kinds of mistakes that are unforgivable. You guys are well, except for that I'm giving you partial credit, so they are slightly forgivable. But these are mistakes that I don't want to see. Why would you add those two numbers together? If you add them together and get an answer of 7, where in algebra did you ever have to add those two, right? So be careful. If you make mistakes like that, I can't give you the 5 out of 5, but if you make a simple error somewhere in a problem, then I can. So just be careful. That's, I don't know, moral of the story. Anyway, last step here, get rid of the 20, multiply it to the other side, and you get m equals 0.2 kilograms. Remember that you're only required to put the units if you do a makeup test. Lori, did I cover that okay? Good, good. And I feel like I sounded too much like a jerk on that last part on this stuff. Please don't get your feelings hurt if you made a mistake like that. I'm just telling you that I'm not going to give you 100% on something. I'm only going to give you 100% on a mistake if all of the steps are right. It's just that something happened that's not that big of a deal, right? But you can still get a 4 out of 5 on a problem like this, so it's not that big a deal. All right, point 2, that takes us to today's notes. Finally. Yes, we wanted to go over, when we're done with notes, it was asked earlier in an email for me to go over the last part of the lab that was due yesterday, so it would be worth us going over that because there's a chance that that's going to be one of your test questions. With the at-home learning, I prefer to make the labs the test questions because then those people who actually did the labs at home have an advantage over the people who didn't. And also then they have them in front of them so they could kind of copy what they did to solve the lab. They can use that as help for them to be more successful on the test. That lab that you guys did with sliding stuff with friction that was due yesterday, I would never put that on a test if we were in school because without notes, that's too hard of a question. Those of you who are juniors and might take AP Physics next year, now that story changes. You could see that as a test question. You're not supposed to be listening to me right now. You're supposed to be copying down the notes for today. So let's give you a moment to do that. Most everybody is familiar with Newton's third law. This is a good time for me to read all of your chat stuff. Make sure that the girls aren't being too mean to Hunter. There's nothing strange about the letters F, U, and K being in the same sentence. That doesn't mean anything, right? There's subscripts, commas, and a letter missing. But I will say this: if you are a kind of person like me that uses word association to remember things, if you're using bad words as a way for you to remember things in your own head, there's nothing wrong with that, right? It's the important thing is that you remember it. But with this class being on right now distance learning, you don't have to remember stuff so much like that. I wasn't mean like you guys were to Hunter. I was only mean to Hunter when he deserved it. You guys are just mean to him, period. I'm not mean to anybody. I just point out facts, right? So like, for example, when I last year wrote on the whiteboard, if you can see that, where it says, in Canada, don't they speak Canadian? I was just stating a fact, right? I wasn't being mean to anybody.
I just call it being brutally honest.
Yeah, I know. All right, so for every action, there's an equal and opposite reaction is what you guys know from Newton's third law. You've already heard that before. And of course, that phrase really is applied more philosophically in real life, right? For every action, there's an equal and opposite reaction. It's just basically your parents trying to tell you, don't do things that are wrong because then bad things will happen to you, right? If you steal something, then something's going to get stolen from you. So that's good lessons in life. But the term came from physics because of Newton's third law. And really, what's put in parentheses is the all-important word, is that for every action force, there has to be somewhere in the universe an equal and opposite reaction force. Now, we're not going to look at problems that involve the entire universe to have something that actually cancels out the force that's applied. We're always going to keep them right next to each other. So for example, we have a nice picture of a 100 kilogram football player and his 70 kilogram girlfriend that are ice skating, and they push off of each other, okay? Now, when they push off of each other, what happens is the boy pushes on the girl. We're going to call that the force of the boy pushing on the girl. Yes, so now if Hunter's going to make a comment about F and K and all of that stuff, we could also say that there's a bong in this problem. It's just letters, right? But then that there's an equal and opposite force of the girl pushing on the boy. So a gong, I don't know what that is, but those are equal and opposite forces. Okay, so then what would you say about Mexico? In Mexico, they don't speak Mexican, they speak Spanish. It might be a slightly different dialect. In Central America, in Honduras, they don't speak Honduran. Guatemala, they don't speak Guatemalan, they speak Spanish, right? So certain languages, you can't try to defend Canadian, they speak French or they speak English. But that's beside the point. We were just trying to point out that we point out facts in this class. What we see happen here is when there's a force exerted. So according to the way this is written is the football player pushes on the girlfriend. That seems kind of rude the way this question is written up, but it's your textbook that wrote it that way, so I'm going to take myself out of it. If they both push off of each other, one of them might be exerting more of the force than the other. And like I said to you on the notes, if you already read them or if you're seeing them right now, don't be sexist and assume that the person that's bigger or the person because they play football pushes harder. They might not be stronger. They might not even be pushing that hard. The important thing for us to know is however the two of them contribute to the amount of force of pushing each other apart as they go skating off, that total amount of force is exerted on both of them equally. There is a question that I offer as extra credit second semester. I don't know how this is going to work yet, but what the picture shows is a horseshoe magnet. It's a really large one, really large horseshoe magnet, and it's got a little tiny thumbtack stuck to it. And the question asks you, which of the two objects is exerting a larger magnetic force on the other? And it's trying to get you to say, oh, the horseshoe magnet, of course. And the answer is not the horseshoe magnet. The answer is it's equal and opposite. They both contribute to the magnetic force, because if this thumbtack was made of plastic, it's not going to stick to the magnet. So therefore, there's no force there. They both have to contribute, okay? We know that the large magnet probably contributed more to the combination, but still the amount of force of attraction between the magnet and the thumbtack is equal and opposite, all right? Same thing here with our picture with the boy and the girl. The amount of force on each is equal and opposite. Now, as they push on each other, there's unbalanced forces. Normally, I would even want to draw this where like maybe we should put that the force on the boy is a different color than the force on the girl. Problem is the green doesn't show up through his nice shirt. But you can kind of see that. You've already drawn it anyway, so it's okay. If you have an unbalanced force on an object, that object's going to accelerate. And so even though these two forces cancel out, they're acting on different objects. The one that acts on the boy causes the boy to accelerate. The one that acts on the girl causes the girl to accelerate. And so we really end up with a Newton's second law inside of Newton's third law that says that that mass that has a net force acting on it causes that object to accelerate. So a 100 kilogram boy gets an acceleration that's less because he has more mass. A 70 kilogram girl gets an acceleration that is more because she weighs less, right? More acceleration when you have less mass, less acceleration when you have more mass, such that they both have to be equal to each other. Solve for A, you're going to start by multiplying. Can you believe who wrote this textbook question? I think they were diabolical. Isn't 70 times 6 420? And we just had force of the boy acting on the girl's bong. I think there was something going on when somebody wrote this question. They were trying to make a joke. That doesn't matter. It's not a funny joke. It just is what it is. But it does come up to be 4.2. I put lots of great notes. When you look at these online, I broke these up into many, many slides rather than just 2. So if there's anything that I've said that just didn't quite make sense, go back and look at the slides and see if you can kind of figure it out. And then if you can't, of course, you can always email me and we can talk it over and get it figured out. But probably after a few of these examples, you're not going to need anything extra. Example 2. Example 2 and 3 are supposed to blow our minds. That's because you don't realize something. When you, right now in your bedroom or in kitchen or living room, wherever you're taking your notes right now, if you get all excited about example 2 and you jump up in the air, you don't realize that while you jump upward, you also push the earth downward. That's actually what you do, is when you jump upward, you don't actually cause yourself to move upward. What you do by bending your knees and then accelerating up, what you're really doing is accelerating the earth downward. So when you jump, your legs exert a force on the earth, causing the earth to accelerate in the opposite direction. Meanwhile, because forces have to be equal and opposite, the earth has to push up on you with a force that is equal and opposite to the force that you exerted on it. So both things then have to accelerate. The mass of the earth times its acceleration has to equal the mass of the guy times his acceleration. Now, we'll solve this so you can see that it really doesn't matter. But technically, it's there. The mass of the earth is 6 times 10 to the 24th power times its acceleration. The mass of the guy is 50 kilograms times his acceleration. So 50 times 3 is 150. You're going to divide the 6.6 times 10 to the, not negative, 6 times 10 to the 24 to the other side. And you're going to get an extremely, extremely small acceleration. I'm not going to give you a question like this one on your test. This is worthless because that acceleration right there doesn't matter. A hydrogen atom has a 1 proton in its nucleus and 1 electron on its outer energy level. This has a radius of something to the magnitude of times 10 to the negative, I think it's 10 to the negative 11th power in meters. So when we talk about the acceleration of the earth downward in a fraction of a second, how much time does it take for you to push on the earth? Maybe let's say you do it for 1 full second. The amount of acceleration you give for the earth is like a billion times smaller than the width of an atom. So we're not talking about enough acceleration to be consequential. So of course that always leads my classes to ask, what if everybody was all on one side of the earth and we all did it at the same time? You would still find out that the entire mass of everything that can exert force on the earth, all the animals, all the cars, all the rocket engines, everything. If you put everything on one side, nuclear reactions, explosions, nothing could actually knock the earth out of its orbit because it's just got way too much mass, right? We're talking about 24 zeros after the 6. That's a lot of zeros. I'm not even counting, so I don't even know when to stop. I'm just doing this for effect, right? Just too much mass. So technically the earth accelerates, but not enough to make it worth a test question. If we're going to give you a test question, let's give you one like this one, because now we get something that's actually substantial. Okay, so with that in mind, I don't know that we need to do 4 examples today. How about if we do 3 examples and you're going to skip example 3? So don't copy this one down. I just want to say to you, if a person is skydiving on the moon, the reason why they free fall towards the moon with an acceleration of 1.7 meters per second squared is because of the gravitational attraction. While they're accelerating downward, the moon is accelerating upward because the astronaut, capital A, exerts a force on the moon that's equal and opposite. So those two forces cancel each other out, but because they're acting on different objects, each one is moving, each one is accelerating. But by how much? That's why I'm having you skip this one, is because once we put the numbers in here, you see that the acceleration is still extremely small. Okay? Now, what we might have as an issue for students is, do you know how to plug all of this stuff into the equation? Because you might not care about the physics ramifications. You might just be thinking, how do I get my good grade on my test? So that's why I want to do at least one more example where we take our time on this one here. Plus also this is still the Earth. So it's still not a very good question. I think it's in the homework tonight where we do something on an asteroid. And that brings us to, I bet you I was the only one in class last night watching Nova on the Osiris-Rex landing on the, I can't remember what the name of the asteroid is, like Brunner or something like that. They landed on an asteroid just recently and they took a sample. What they did is they landed on it and basically took like a vacuum and sucked up a bunch of the basically dirt that was on the surface of the asteroid. And then they're going to bring it back to the Earth and analyze to see what's there. But just like the movies like Armageddon, if you have a small enough asteroid, it would be easy for us to knock it off a course that would be like maybe if it was going to collide with the Earth, because all we have to do is just go put something on it, like a small rocket engine, and we could easily cause it to deflect enough away that it doesn't hit the Earth. But it's got to be a small enough mass that that rocket would actually have an effect. In the problems that we're seeing, for examples, 1, 2, 3, 4, I guess 2, 3, and 4, we're dealing with something that's not really effective, right? Because we're dealing with such a large Earth. Okay, but why I like this question also is because if we say that the force of the truck acting on the Earth, now when you step on the gas pedal, even if you cause your tires to start to spin, what happens there is that's not what moves the car forward. What you do by stepping on the gas pedal is the tires actually spin the Earth underneath you like a hamster wheel. While it spins underneath you like a hamster wheel, it exerts a force on your truck or car that's equal and opposite that causes it to move forward on the surface of the Earth. So your gasoline engine is not what moves the car. It's the gasoline engine moves the Earth, and then the Earth moves the car. Kind of crazy concept, isn't it? But in the end, you guys only care about one. I mean, I know you care about more, but you also care about being successful on your test. So you recognize by the way these questions are worded that this is a Newton's third law problem, right? They're going to give you two objects. They're going to talk about accelerations, except for this one. This is why we're doing this one. Doesn't completely talk about the acceleration. So let's start with this. Mass of the Earth. What we do is whatever it's acting on, that's what we write down the mass of. Over here, mass of the truck. Even if you put it backward, it wouldn't matter. Okay? And then the money question is, what's the acceleration of the Earth? That's what we're solving for. The mass of the Earth was given in the last problem, or example 2, actually. We're almost done. You know what? We have a little bit more to go over, don't we? Because we have to talk about a mid-chapter review also. 6 times 10 to the 24th times A equals mass of the truck, which is 1,000. And then we run into our first problem. They didn't give us the acceleration of the truck. But here's what they did give us. They said that after 3 seconds, it's got a speed of 12 meters per second. That implies to me that it probably started from, it even says it, starting from rest. VI is 0. Using the green information, is there a way for us to find the acceleration? Sure, it'd make a good test question, wouldn't it? Because it combines chapter 5 to our chapter 6 material. Really makes a good final exam question. You have to start by taking the motion variables. Now, if I gave this to you as a test question, I would actually break this up into multiple parts. I would say, part A, find the acceleration of the truck. VF equals VI plus A times T. 12 equals 0 plus A times 3. Here's a good time for me to say to you, the answer is not 9. The answer is not 15. You have A times 3. So to get the A by itself, you have to divide both sides by 3. Okay? So be careful on that, but show your work so I can at least give you maximum partial credit. In this case, it comes out to be 4. Now that we know the acceleration, I can plug that in right here. And then I can solve for the acceleration of the Earth. How much did you spin the hamster wheel? Well, not much. 10 to the negative 22nd power. What if everybody put all of their cars, then we wouldn't even have to gather on the same side of the Earth. What if everybody, we planned on at one particular day, at one particular moment, everybody faced their cars to the east and we all gassed it? Could we cause the Earth to spin a little bit faster so that a day, instead of being 24 hours long, was dropped down to like 23.5 hours long? Theoretically, yes, we could. But realistically, no, we can't, because there's just not enough mass of cars and people and everything else to affect that very, very large mass of the Earth. Yes, I have these on opposite sides from the previous slide, but it still works. Okay? That's chapter 6, homework number 7. You have a second assignment to do tonight. The second assignment to do tonight is also to do your mid-chapter review. Now this has like 6 questions, or maybe 7, but it's basically practice of the things that we've done up until this point. So don't just jump straight to the slides to look to see and copy down the answers. That's only worth 2 points. You need to make sure that you can answer these questions, right? Go through this and say, okay, could I label the forces that are here? Do I understand what's going on? And then go from there. All right? But I will stop because we spent so much time on the homework today that we'll just go over all of the mid-chapter review, 6 questions, along with these 4 questions on Monday. Okay? I am going to start letting you check out as you want to leave, but I did get a question about how to solve for that last part of the lab, so I'm going to go over that right now. All right, so Hunter, in case you see this on your test, you have an object that is sliding across the ground, and we recognize that as it slides, it's coming to a stop. So therefore, if it's coming to a stop, we measure this distance here, and I'm not sure why I'm putting a 5, but I'm going to just keep putting a 5. I'll just make the math easy for myself and say that the distance that it slid was 5 meters. 5 meters, 5 meters. And we'll say that it took a time that t equals 2 seconds in order to do that. That's kind of realistic for the things that you guys had. Now, step number 1, I know you already know how to do this. We use the equation distance equals VI plus VF times T, which meant 5 equals 1/2 of VI plus 0 times 2. And then that really ends up meaning that the VI had to be 5. I didn't want numbers to come out to be the same, but it's too late now. That's just the way it works. Some people, if there's any other people who are listening right now, looks like a few of you are still here, got this part wrong, and I maybe took off a point for that, but then even though you used that wrong answer the rest of the way through the problem, you didn't lose any points for it. So if that happens on a test, that would still be true. Okay, then the next thing is VF equals VI plus A times T. So 0 equals 5 plus A times 2. Solving for the A, you're going to move the 5, which makes it -5, then divide by 2, which gives you -2.5 meters per second squared. Okay, now where we get to the part where you had the question, Hunter. So in our free body diagram, the forces that are here are the friction force and the normal force and the gravitational force. Okay, those are the only forces that are present. So if we make an F-net equation, my F-net equation says the only thing that's affecting the movement in the forward direction is this negative friction force. F-net is Newton's second law. It's mass times acceleration. And then the friction force has the formula mu times Fn. So these are the steps that I kind of sent you one big picture of on your email. Now, we don't know the mass of the object. Some did because they were able to weigh them on food scales, but most of us don't, and that's okay because it'll cancel out. So we've got m times negative 2.5 equals negative mu times, and then now for Fn, because that's equal and opposite to Fg, we can substitute in Fg. And then Fg has the formula mass times gravity. So that's how we get to this point right here, which is the all-important step, because now what that allows us to do is cancel out the mass. So all I have left is G, and G is gravity, 9.8. Okay, so now we've got negative 2.5 equals negative mu times 9.8. Obviously, get rid of the negative signs, and then just divide the 9.8 to the other side, and you get mu equals basically about 0.25 for this one, 0.25-ish. That was it, yes. Okay, and I did explain it out in a homework, and I also explained it out in a lab. But still, if that wasn't enough, if that was still not enough for you to understand the steps, this is why I am giving you a full week to turn in the labs. So that if you do the lab on Saturday, then you can ask me the question on Sunday, and I can send you an email. You say to me in the email, I still didn't get it. Then on Tuesday, we go over it, and then you can turn it in on Wednesday. But I'm not going to do that unless you ask for it. So just keep that in mind for the rest of our labs that we have. Your pendulum lab, I mean, that could be a question if there's somebody has an issue with the math. If you, Hunter, if you have a problem with not being able to go to normal school, you know what? Transfer to Lucerne Valley High School. They're open, right? If you want to go there, go for it. Stop complaining about things that are out of our control. There's nothing that we can do. So we make the best of what we have here. So, you know, you can say, well, if we were a normal school, that we could all work together on this. Yeah, maybe. But what happens if you bring in, give me COVID, and I'm out for 3 weeks? Then you'd be learning this from some substitute that doesn't even know how to do it, period. So at least you got this, right? So yeah, you might not get immediate gratification via distance learning, but at least you still get you now know how to do it. That's what the whole point was, right? So, it is what it is. So anyway, so now you know what to do, because if you got, obviously, Hunter, you probably only lost maybe 2 points on this on your lab. So an 8 out of 10 is still a B. Then when you do this on your test, if this question's on there, now you're getting a 10 out of 10, right? And then on a test, of course, when you put that into 100%, it ends up being worth more points. So it's more important that you can do it so that you're successful on your test. But how about do this lab, the pendulum lab? Don't wait till the last minute. And then if you have any issues, we can clear them up before next Wednesday. Anybody else have a question before I close all this up? Good. All right. You guys have a wonderful rest of your day, and I will see you on Monday.
Bye-bye.
All right.